Welcome to Tech Travels, hosted by the seasoned tech enthusiast and industry expert, Steve Woodard. With over 25 years of experience and a track record of collaborating with the brightest minds in technology, Steve is your seasoned guide through the ever-evolving world of innovation. Join us as we embark on an insightful journey exploring the past, present, and future of tech under Steve's expert guidance.
Hello and welcome back to another exciting episode of Tech Travels. Today we're diving into a topic that's generating a lot of buzz recently, quantum computing. Now, after the incredible response that I received from our last episode with Dr. Thomas Wong, many of you had reached out asking for more content on this groundbreaking technology, and honestly, I just couldn't have waited. I couldn't be more thrilled to have delivered. But before we dive in, I first want to take a moment to just extend a huge thank you to all of our listeners and subscribers. Since I started this podcast back in February, it has been an incredible journey, and I couldn't be more appreciative of the support. Your enthusiasm and engagements have really made this experience truly rewarding, and I'm really excited to continue exploring these fascinating topics with you. And in today's episode, Quantum Computing from Theory to Reality, we're going to break down this complex subject in a way that's a little bit easier to understand and digest. If you're familiar with my episode 1 on AI down to basics, this is going to follow a very, very similar format. So let's start exploring quantum computing and how it works, why it's such a game changer, and let's explore this fascinating technology together. So let's start with the basics. Quantum computing is built on the principles of quantum mechanics. And this is really a field of physics where it began to take shape in the early 20th century. But to understand why quantum computing is so revolutionary, we need to step back into the origins of quantum mechanics. Now, I promise this is not going to be a physics class. The story of this really begins at the dawn of the 20th century. Now, classical physics had dominated scientific thought throughout many, many years, for centuries almost. And this was really fascinating because it really presented serious challenges to explaining certain phenomena. Now, in 1900, a German physicist by the name of Max Planck had made groundbreaking discovery while working on a topic around researching black body radiation. And this is where the objects emit and absorb energy. And Max proposed that energy is not only just emitted continuously, as classical physics had suggested, but in discrete little packets, which he had called quanta. And this was really the first hint of that the laws around governing the microscopic world of atoms and particles were fundamentally different from those of the way that we experience them every day. Now, another scientist, I'm sure you know, Albert Einstein, had extended and explained on what Max was trying to do. Max Planck's idea was basically, he was explaining that the photoelectric event is where light striking a material causes it to emit electrons. But Einstein took it a bit further. He said, well, yes, that's true. Light is made up of quanta, now called photons, which we both have, both particles and waves. And this was interesting because the duality was one of the first indications that the quantum world operates on rules that defy classical intuition. Now, over the next few decades, other pioneering scientists, including Niels Bohr, Werner Heisenberg, Erwin Schrödinger, they all contributed to the development of quantum mechanics. But it wasn't until Niels Bohr introduced the idea of quantized energy level in atoms. Now, Heisenberg also saw something different. He started to look at this and say, he's going to formulate what they call the uncertainty principle. Now, Schrödinger also developed basically a wave function that basically is used to describe the probabilities of a particle's location. Now, these developments collectively established the foundation of quantum mechanics, which is just simply a field that describes the behavior of particles at the atomic and subatomic levels. All right, we got that. As the particles of quantum mechanics became more established, more and more scientists began to wonder if these strange and powerful rules could be used to harness certain type of computations. But when classical computers started being developed in the 1920s, they were built on something called operating with binary bits. And this was just simply saying, hey, the way it works is that there's units of information that can be either zeros or ones. And these bits follow the classical physical laws, or basically the classical laws of physics. While they have while they're very powerful, they still face limitations in dealing with problems that involve massive amounts of data or other complex systems. But this is where the idea of quantum computing really comes into play, because in the 1980s, physicists like Richard Feynman and David Deutsch realized that a computer based upon the principles of quantum mechanics could, quote unquote, in theory, perform certain calculations much faster than classical computers. And the key to this speed lies in the quantum bit, or the qubit. So when we look at the birth of quantum computing, we have to really look at it through Feynman's vision. Now, the 1980s, this study of quantum mechanics had already really started to transform our understanding of the physical world. And scientists were more and more discovering that there's this strange and counterintuitive behavior within particles at the quantum level. And these behaviors are really what defined the classical physics to be used pretty much every day to describe things like phenomena or the motion of the planets, or even something as simple as the flow of natural bodies of water. However, they really developed deeper into these quantum mysteries. It became clear that simulating quantum phenomena using classical computers was really an insurmountable challenge. And the reason why, of course, back again, is that classical computers just operate only on binary bits, which can either be a 0 or 1. But the great thing about quantum was quantum doesn't follow such simple rules. And this is where Richard Feynman really kind of comes into the picture. Richard Feynman, who was already very well known in the scientific community, particularly for his work in the 1940s at the Manhattan Project, where he played a critical role in the development of the atomic bomb during World War II. And his contributions to quantum electrodynamics earned him a Nobel Prize, which he was celebrated for his ability to explain complex topics in a way that others was very difficult, and it was very easy for them to associate to others. Richard Feynman had given many lectures at the University of Southern California, and many of his lectures can still be found online today, even 40 years later. If you've not checked out any of his earlier works, I definitely highly encourage you to take a look and look for his lectures on how fire is developed. It's truly eye-opening. Now, during this time, Feynman recognized that the limitations of classical computers when they were trying to simulate quantum systems like the behavior of molecules and atoms. He proposed a very radical idea to simulate quantum phenomena accurately. And in order to do this, we would need a new type of computer that didn't just model quantum behavior. It had to actually operate according to the principles of quantum mechanics. So in essence, he really envisioned a computer that could harness quantum effects like superposition and entanglement, and he really wanted to use these to perform calculations that were far beyond the reach of classical machines. Now, back in 1981, Feynman proposed the concept of a quantum computer at the first conference of the Physics and Computation conference at MIT. And he introduced the idea that such a computer could harness the principles of superposition and entanglement using quantum phenomena, and really to perform this in a way that classical computers could not achieve, no matter how advanced they become. And really it was because of this event, this is really when it started to mark the birth of the idea of quantum computing. Now, Feynman's idea was not just about increasing computational power. It really was about rethinking how computation itself could be leveraged by using very similar principles of quantum mechanics that govern the behavior of the smallest particles in our universe. And now at this point in time, this was absolutely groundbreaking. It was groundbreaking. It was a groundbreaking moment in the history of computing because it laid the foundation for what we now know and as we now call quantum computing. Now, this is a field that is still very early in its stages. And the promise was that it was going to revolutionize the way that we approach complex problems. And instead of being limited by classical logic and classical binary states, quantum computers could, in theory, explore a vast number of possibilities simultaneously, making them extremely powerful to do certain tasks. So after Richard Feynman kind of proposed the concept of quantum computing in 1981, the field began to attract more and more attention, and this led to significant advancements throughout the 1980s and the 1990s. And the way that we look at this is, okay, well, what were some of Feynman's ideas and how did those kind of move into other additional groundbreaking developments into the 1990s? Well, in 1985, David Deutsch, who was a physicist at the University of Oxford, he introduced a concept called universal quantum computing. Now, this was a pivotal moment because what it is Deutsch's work demonstrated that quantum computers could theoretically perform any computation that a classical computer could, but just simply a lot faster. And his idea was built on the principles, again, of quantum mechanics. And this really suggested that a quantum computer could harness things such as superposition, phenomena, and solve things that classical computers could not do simply in the current form. And the significant work of this, of course, lay in the introduction of the quantum Turing machine, a theoretical model that extended the capabilities of the classical Turing machines to the realm of quantum computing. And if you remember in my first episode, I went into detail around Alan Turing and his amazing work with the Turing machine and how it broke basically the German encryption in World War II called the Enigma machine. So looking at the 1980s and 1990s, there were a lot more groundwork that was actually being done. More research was coming into the field. Researchers such as Ralph Laudner and Charles Bennett from IBM, they really started to explore something new. They started to explore how quantum cryptography and information theory could really expand around the potential around expanding applications for quantum mechanics in this specific technology. And it was also a time at which another researcher by the name of Peter Shor basically came out in 1994 when Peter Shor, who was a mathematician at AT&T Bell Labs, he developed an algorithm that could effectively factor large numbers. This is known as an algorithm, or known as Shor's algorithm. And what it did was it demonstrated that a quantum computer could solve problems. And it could also solve problems such as breaking widely used RSA encryption that were practically unsolvable by classical computers. Now, Shor's work was really a turning point because what it did was it moved quantum computing from a theoretical possibility into a practical threat to existing cryptographic systems that use modern day encryption. And this is really what happened is this really sparked a lot of interesting interest and urgency in the quantum computing research. And as these implications are for around security and privacy, they found them to be extremely profound. Also at the same time, another researcher by the name of Les Grover, who was a database specialist, and he was searching in 1986 for another prominent capability within quantum computing that he could use basically what they called unsorted databases and see how they could work faster by using basically quantum versus classical computing. Now, Grover's algorithm was overshadowed by Peter Shor, but they were nonetheless absolutely critical for the development of quantum. And what it did was it provided a clear example of how quantum computers could really just outperform classical ones beyond cryptography, and just really kind of highlighted a more profound and more broad potential for just how quantum computing could be used in the future itself. But despite these theoretical breakthroughs, the progress of quantum computing during the time of the 1980s and 1990s, it really started to face a lot of several obstacles. Some of these are going to be things like, well, technical challenges. Most of the significance and the barriers was the immense technical difficulty involved in really building a quantum computer. And a quantum relies on qubits, which are extremely fragile. They require conditions that are very difficult to achieve and maintain, and you have to keep them in extremely low temperatures. So the challenge became really, really difficult, so where qubits start to lose their quantum state due to environmental interference. And this made it really difficult to perform, reliable computations, because the technology itself had to control and manipulate the qubits with precision simply that just wasn't available at the time. You also have this thing known as error correction, and early forms of error correction was still in its infancy. We didn't really know how to deal with that. But these technical hurdles really meant that, even despite the theoretical advancements, there was still some progress, but it was still progress that was still so very, very slow. Another limiting factor was, the funding. There was funding limitations, and the funding was another critical issue. And while there were some government and institutional support, particularly in agencies like DARPA, the field of support pretty much came from modest institutions, areas of research. Some money came from the semiconductor industry. Some came from other classical computing companies. And really, even the U.S. government, they did recognize the potential and strategic importance of quantum computing, especially when we're talking about cryptography. But funding was also very limited to exploratory searches and areas of research, rather than more of a large-scale type of funding and more of the large-scale development projects. Another thing, of course, that was also limiting was some of the academic institutions. They really struggled to understand and really secure consistent funding for quantum computing research. And again, it was started to look at as, well, this is a very highly speculative and long-term endeavor that did not have any real immediate practical applications. Now, during this time, if you look at it, kind of what was happening in society and other academic perspectives is, during the 1980s, 1990s, quantum computing was kind of this largely esoteric type of field. It was really just kind of mainly used by physicists and mathematicians. And the general public, people were really largely unaware of really what quantum computing did. Outside of the academic world, people really didn't have much of an idea. It was seen as, hey, this is really cool, but there's a lot of theoretical curiosity rather than a real practical tool. And the perception really kind of hindered the field's growth, because as it was trying to justify its existence, it was really meant with skepticism. People found it very difficult to understand, and the investment in the technology just didn't believe that it was going to be something that was going to be here. They looked at it like this was something that was going to be decades, if not multiple decades away from any real world application. Now, aside from that, if you look across, at what was happening at this time, you look at cultural influences in science fiction. And I think this is where the cool part is that when quantum computing really struggled to gain traction in the real world, the idea of having these advanced computing technologies was really kept alive in the public imagination through things like science fiction. I remember growing up as a kid in the 1980s. I feel like this was kind of the golden age for science fiction. And then even into the 1990s, you explore popular themes such as, advanced technologies, artificial intelligence, and virtual realities. So you think of movies like The Matrix or Terminator 2, as well as, even my own favorite television show, which was Star Trek at the time. Star Trek Next Generation really captured, the public's influence and helped them kind of maintain an interest in broader possibilities of quantum computing that really kind of kept the door open for the eventual rise of quantum computing. And I think this is even cool because, even the specific concept of quantum computing, even though it was not widely understood, people loved the idea of having something that could be far breaking or just simply just far out there in the computer world that would really just kind of be next level as to what they were seeing on science television. But if we look at the government, well, that's a different story. The government, and of course, had these, they had regular, institutional roadblocks. Now, there was also a lot of hesitation within the U.S. government and the U.S. military establishments regarding quantum computing. And while the potential for quantum cryptography and quantum computing were recognized, there were concerns about the security implications of such a powerful technology, which could really disrupt existing encryption methods. Additionally, they were also very uncertain around the timeline for quantum computing, its development, and really and that's really what made it a very low priority compared to more immediate technological needs. But as we start to kind of round out the end of the 1990s and we start kind of getting into the late 90s, early 2000s, the end of the millennium really started to set the stage for the 21st century, because at the end of the 1990s, quantum computing was really kind of poised to be the next phase of development. Now, researchers had laid a solid theoretical foundation. They demonstrated key algorithms which began addressing the practical challenges of building quantum hardware. And again, in the late 1990s, they also saw companies also start to form systems like what they called the D-Wave system in 1999, which was really aimed to commercialize quantum computing technology. And this is where we start to set the stage for rapid advancements in quantum computing that would follow all the way into the 2000s. So as we move from theory to small-scale experiments, where we actually start looking at quantum processors and the exploration of quantum supremacy. So just as we've explored the origins and early developments of quantum computing, I think it's clear that this technology really isn't just a local phenomenon. It really is a global race. If you look around the world, countries and companies are heavily investing in quantum research. And really, this becomes a transformative field, because you start to really appreciate the global landscape for quantum computing. We really need to consider not just the technical advancements, but also the broader other societies and the perspectives, government initiatives, and other challenges that lie ahead. Now, the United States by far is leading the way as part of, some of the tech giants within the United States. Companies such as IBM, Google, Microsoft, these companies are at the forefront of quantum computing, both in research as well as development. Now, IBM has particularly pioneered making quantum computers accessible through their cloud or via their IBM Quantum Experience platform. And this initiative really kind of helps democratize access to quantum computing, because it allows researchers, developers, and even students from around the world to experiment with quantum algorithms, and they can use that to contribute to the growing body of knowledge around quantum computing. Now, also, Google had made significant impact in the year 2019 when it announced that a quantum computer had achieved quantum supremacy. And there's that word again, quantum supremacy. And this really just basically means that their quantum processor, the Sycamore, performed a calculation in 200 seconds that would have taken the most powerful classical supercomputer of its day, thousands of years to complete. That's pretty crazy. But this achievement really was a milestone that demonstrated the potential for quantum computing and how it can really lead to solving problems that are really, really intractable for classical computers. So if we look across Europe to see what's happening there, so across the Atlantic, they're also making significant strides in quantum computing. The European Union's first quantum flagship initiative launched back in 2018. This is a €1 billion 10-year project, and it really is aimed at really kind of advancing quantum technologies across the continent of Europe. And even though this is an ambitious program with one of the largest and most comprehensive efforts to develop and build quantum technology, they have had over 5,000 researchers from academia and other industries to kind of help work and collaborate on this immense project. Other countries like Germany, the Netherlands, and Austria are also home to some of the most advanced quantum research institutions in the world. So for instance, the University of Innsbruck in Austria is renowned for their work in quantum simulations, and Delft University and Technology in the Netherlands. They're also another leader in quantum cryptography and quantum networking. And these institutions are really just not pushing not only the boundaries of quantum science, but they're also contributing and collaborating with other industry partners. And they're using that to really kind of translate that research into distilling it into practical applications. Now, China, they're also a major player in the global quantum race. China has emerged over the last couple of years as a major player in the quantum race. Most recently, they invested heavily in both quantum computing and quantum communication. Back in 2016, China launched the world's first quantum satellite. And this satellite is capable of conducting what they call QKD, which is quantum key distribution, over long distances. And that technology could also really revolutionize how secure communications can be by making it virtually impossible to hack. Now, the Chinese government has also prioritized quantum research as part of its broader strategy to become the global leader in the high-tech field. And it's really kind of based upon their ability to establish multiple partnerships with other national laboratories dedicated to quantum information science. And that, of course, needs, like anything else, needs to have funding, billions of dollars to fund into these research and development fields within quantum. And I think that what this really shows is that their support and strategic importance is very important, because it really places China on a quantum technology shift where it's not just a scientific advancement, but it's also for their own sense of national security. And now Canada also as well. Canada has got companies like, again, I mentioned earlier, the D-Wave systems, and this is really commercialized quantum annealing. And that really is just simply a form of quantum computing that's particularly effective for solving optimization problems. And Canada is also home to Quantum Valley initiatives in Waterloo, Ontario, and they support quantum research as well as commercialization efforts. And this has really kind of been a central hub for most of the world-class talent and investment in making Canada a real hub for quantum and quantum innovation. Now, the government within Canada has also recognized the importance of quantum technology, and they've also supported its development. And in 2021, the government announced that the creation of National Quantum Strategy, and this really kind of puts a framework around finding substantial funding to really boost quantum research, improve talent development, and also look for industry growth as well. And I think the really cool thing about this is that this really highlights, our partners to the north, the Canadians' investment and their commitment to maintaining their competitive edge in this rapidly evolving field as well. But over the last 20 years, the public awareness of quantum computing has started to increase. And although it still remains a highly specialized and very complex field, it's also one that's really misunderstood by the general public. So for many years, quantum computing is seen as very distant, almost science fictional style type of concept with very, very little immediate relevance to everyday life. Now, companies like IBM, Google, they've all made headlines and have had recent advancements around quantum computing, and some of that has really started to lead to the perception of quantum computing has started to kind of maybe shift the needle a little bit. But it's also worth noting that science fiction, it's my favorite topic. Science fiction has also played a critical role in keeping the public's imagination really open to the possibilities. You think, again, I reference movies like The Matrix, even movies like Inception, has really explored themes of complex, reality-bending type of technology. And I think this resonates a little bit because these strange and counterintuitive nature of quantum mechanics kind of plays into these movies' centralized theme. And I think these cultural references kind of also bridge the gap between the highly technical world of quantum computing and then also to the broader public, just making the concept more relatable, even if it's not fully understood. Now, the government has started to look at investing heavily in quantum computing, and this was not always the case. Because during the early stages of quantum computing, government funding was very, very limited. The technology was often seen as very long-term, it was high risk, and it had very uncertain returns. Now, the potential applications for quantum computing, particularly around cryptography and national security, those are the ones that have become more and more apparent and more attractive to the government's interest in funding because of that particular segment where we now start to see more and more funding increase for things like cryptography and national security. So just for example, as the U.S. government passed the National Quantum Initiative Act in 2018, which provides over $1 billion in funding for quantum research over the next 5 years. Now, also, the European Union has also kind of done the exact same thing. So the European Union, through its quantum flagship, China with its national quantum initiatives, they have also made substantial financial commitments to advance quantum technology. But still, despite the efforts, that these roadblocks still remain, the technical challenges of building stable, error-corrected quantum computers are very, very formidable. And there's still a long way to go before quantum computers can really fully integrate into mainstream applications. So again, the geopolitical implications of quantum technology, particularly the impact it has on cybersecurity, has really started to kind of elevate the concerns around a quantum arms race. And this is where nations are competing to develop quantum capabilities, potentially leading to new forms of basically technological inequality. But I think about this for a second and I think, okay, so there's got to be a philosophical aspect to this. And if we take a step back again and just look at quantum computing, I think quantum computing really as it starts to develop, it also raises, important philosophical questions also about the nature of reality, of knowledge, and the future of humanity. Quantum mechanics, I think, really underpins quantum computing, and those challenges our traditional, and it really challenges our traditional understanding of reality by introducing concepts like superposition and entanglement. And this is really where particles can exist in multiple states simultaneously and be connected across vast distances. And I think these also have very profound implications for how we understand things like our universe and also our place within it. And I think that some philosophers have suggested that quantum computing could lead to new ways of thinking about the consciousness of free will and the nature of existence itself. So, for example, if quantum computers can process information in ways that are fundamentally different from classical computers, well, what does that say about the nature of intelligence or the potential for artificial consciousness? I think kind of additionally that these are ethical implications of quantum computing that they're still very significant. I think as we develop more powerful quantum technologies, I think that we must consider how we want them to be used and who will be able to control them. Will quantum ultimately lead to new forms of inequality, where only a few powerful entities have access to the technology? Or could we ensure that the benefits of quantum are shared equally and amongst everybody? So as I break it down a little bit, what does this really mean for the everyday person? So I wanted to kind of think about this for a second. Quantum computing might sound like something, only scientists and tech enthusiasts really only care about. But I think the implications could reach far beyond academia and everyday life. So if I look at how quantum computing could impact you in the future across various aspects of daily life, one of the ones that I see this a lot in is basically medicine. One of the most exciting prospects of quantum computing, I think, is really where we start to see its potential to transform medicine, particularly in drug discovery. And today, I think developing new drugs is an incredibly time-consuming and very, very expensive process. And this often involves years of trial and error to really find the right molecular combinations. So traditionally, computers struggle to simulate complex molecular interactions because they require enormous amounts of computing power. But quantum Quantum computers, however, they could simulate these interactions with unprecedented accuracy, and that could drastically reduce the time it takes to develop new treatments. So if I think of a future a few years down the road where medicine, kind of personalized medicine is the norm, treatments are typically tailored specifically to your genetic makeup. Specifically, they could increase their overall effectiveness. And I think quantum computing could also really start to help in the area of designing of new materials around medical devices and in the optimization of things such as medical imaging techniques. And I think those could also be groundbreaking because I think those could lead to earlier and more accurate diagnosis. Now, if I think about it for a second, if I look at another use case such as cryptography, today our world is really protected by encryption methods. And those encryption methods really start to look at, you look at quantum could possibly be used because in today's world, the classical computers, it takes billions of years to crack those, but quantum, it really advances that. These encryption methods become very, very vulnerable. So a quantum computer could solve mathematical problems that underpin most current encryption. And if you think about this, it could basically reduce the time it takes to basically break some encryption. So this is really starting to expose sensitive information such as bank account, personal details, personal emails, even potentially government secrets. Now, while this might sound alarming, it's also driving the development of new forms of encryption. So now we're starting to get into things such as quantum safe cryptography. And that is something where it could withstand the power of quantum computers. And this means that as quantum computing becomes more practical, we start to see a shift towards these more secure encryption methods, ensuring the digital lives that remain protected every day. Another one I can think of is finance. Quantum computing can really revolutionize the financial sector in a couple of different ways. One I look at it is says, it possibly could be that, if you could optimize trading strategies, and you can analyze vast amounts of data at speeds that were just simply unimaginable with classical computers. This could lead to more accurate predictions of market trends. This could also help enable financial institutions, and it really could help drive better investment decisions. And I think that also at the same time, quantum computing can also look at things such as risk management, complex simulations where they look at assets for potential financial outcomes. Now, this is cool because I think this would help enable banks, investment firms, and I think they could also use this to really protect themselves and their clients from financial downturns. Moreover, I think that the shift could also be is that they start shifting to quantum safe cryptography, where it would really be crucial in safeguarding financial transactions around the world. All right, so what about artificial intelligence? I knew this was going to come up. I think artificial intelligence is really starting to transform industries. I think everywhere you look now, you're starting to see something around artificial intelligence, next generation AI or Gen AI. I think AI is already transforming certain industries. I think it's moving from healthcare to retail and many other different industries where it's becoming a disruptor. But I think that the current AI models are limited by computational power. But quantum, I think, could potentially significantly enhance machine learning algorithms, which really are the essential backbone of what an artificial intelligence is. So let me give an example. So quantum computers could process vast data sets that are much faster than classical computers. And this leads to more of an advanced AI model that can learn and adapt in real time. And this really could improve everything from voice assistants to automated or autonomous vehicles. And it can make them even more reliable, more efficient. So in healthcare, quantum enhanced AI could lead to better diagnostic tools that could analyze certain things such as medical images. And it could potentially predict a patient outcome with greater accuracy. Also, if I kind of take a step back and look at things like climate science or climate change, one of the biggest challenges that are addressing right now in climate change is accurately modeling the Earth's complex system, such as atmosphere, oceans, the biosphere. And the current models, which we use today, are really limited by the computational power of, your traditional classic computer, which means that they often rely on approximations and they can't capture the full complexity of climate systems. Now, quantum, on the other hand, quantum could change this by providing computational power needed to really create a more accurate model, a more detailed model of Earth's climate. And those models could really help scientists better understand climate patterns. They could predict extreme or even different types of weather events, and they could develop more effective strategies for mitigating the impact of climate and change or climate impact. So quantum computers could really kind of optimize the design of renewable energies as well. It could look at sources, it could look at how ways to enhance carbon capture technologies, and it really could, and I think it really could play a role in how the global effort goes about combating climate change. And then as you see, even though that quantum computing is still in its early stages, there are a lot of potential things that it could have impact on everyday life, and it could be a huge and enormous impact. So this could be from revolutionizing healthcare, this could be to securing digital world, to enhancing financial strategies, this could be to taking on global challenges like climate change. I think the cool thing is that the possibilities here are very, very vast. And I think quantum computing, as it moves, it's still going to continue to develop, and it's going to influence many more aspects of our daily lives that really kind of bring in both exciting opportunities as well as new challenges. So to me, quantum computing is really more of a way just for us to process, new information. I believe that it is starting to become a gateway to explore, the very nature of existence. And I think also based upon our probabilities, what does it mean for our pursuit of knowledge? How do we approach a world where uncertainty is kind of a fundamental characteristics? What are the kinds of philosophical questions of quantum computing that we should be asking, that we learn to grapple with? Yeah, as a person who thinks about this, I think, with every powerful technology, quantum computing, I think there does come a significant ethical consideration, such as who will control the technology. Will it be used for the greater good? Could it exacerbate existing inequalities? I mean, I think if I want to take a step back, my concern is that we need to develop these systems, that we need to ensure what they're going to be used for and be used responsibly. And this is not just about what quantum computers can do, but what society itself chooses to do with them. And we also need to consider the impact on employment and the economy. Quantum computing could automate complex tasks, potentially displace jobs in certain industries. However, it could also create a lot new opportunities, and this could lead to an emergence of different industries that we haven't even imagined yet. So I think my thoughts overall are going to be pretty positive and optimistic on this, but I think we do need to prepare for the changes. And I think that we also need to ensure that as we advance, we also bring everyone along on this journey rather than leaving some of them behind. So if I put my looking for, my envisioning the future hat on here, I think looking further ahead, I think the ultimate goal of building a universal quantum computer, I think of a machine that can perform any computation any classical computer can, but just exponentially faster. It is truly a game changer, no doubt about it. I think achieving this would be kind of like the transistor or the microprocessor, both of which, sparked revolutions in technology and society. But I think that this is more than just a technological leap. I think this is a leap of how we think and interact with the world. And in my view, I think the future of quantum isn't just about solving bigger and more complex problems. I think it's about unlocking new ways of thinking. It's a new approach to science. And I think that it also opens up new possibilities for humanity. And I think I'm going to use the term quantum revolution. Okay, the quantum revolution is coming. And while I think it's going to change everything, it's also going to change us to be better stewards of the technology we would create. So in my final thoughts, I'll close on this, but I think as we stand on the brink of this revelation, I think it's both exhilarating and also very humbling. I think the possibilities are vast, but I'm also thinking that there are going to be responsibilities with this, such as, will we use the technology to build a better world? Will we let it slip into the hands of those who might use it for less noble purposes? I think these are some questions that I think all of us need to keep asking ourselves as we continue to move forward. So again, I want to thank you again for joining me on the show. In the next episode, I want to dive deeper into how we are also be thinking about the possibilities and what this means for the future industry in everyday life. And I hope that you will continue to join me on this as we explore the fascinating world of quantum and many other deep topics. I also want to take a moment to extend my heartfelt thank you to all of my listeners and subscribers who have supported me in this podcast from the very start. Your encouragement and enthusiasm is really what makes this journey all the more rewarding. So join us next time as we continue to explore the cutting edge of technology. Until then, stay curious, stay informed, and most of all, happy travels.